Welcome back, everybody. We are here today, or wherever we are, or whenever we are, to talk about probability. Now, probability we're going to use as a model of the data generation process. It's a model of uncertainty. It's a model. That's the really interesting thing about probability. You've been using phrases like, oh yeah, that's not likely, that's probable. You may even be using phrases like, I don't have a prior for that, or my prior is really, really small for that, or something. These are scientific terms. They're terms that come from the statistical and the mathematical literature on probability as a model, as a mathematical model. It is probably the most successful model probably anywhere. Certainly the most successful mathematical model. It is used everywhere in statistics, it's used in probability theory, it's used in everyday life now in informal ways. My guess is the first time you said, oh yeah, that's not very probable, you were single-digit years old, maybe before kindergarten. So we're going to learn this, but we're going to learn it as a model. That's the really interesting thing. All right, so let's get started. This is in context. We did overview and logistics, statistical models, data generation processes with simulation and with goats. And now we're going to do probability as a model of the data generation process. So here we go. Probability. Probability is defined. We define probability first with a function. The function is very simple. It's PR of something. So a function, remember, is something where you have an input, you put it in, there's a function, and out comes some results. And so so a square root function is SQRT, open parentheses, you stick something in, you get out something when you're done. So that's a function. Probability is actually a function. PR of something is a function. And the particular function is the probability of data given the model. We'll summarize that as the probability of y given m being the model, y being the output data, same y as we had before. The key thing here is that it's given the model, so we're not going to try to infer the model, we're going to assume the model. So probability is useless with respect to inference, by itself, of course, but it will form the basis of when we switch these around and try to get something analogous to the probability of the model given the fixed data that we have. But here, we're going to be focusing on the probability of the data given the model. So what's in the model? Well, we'll think about the model in the way that we generated it and wrote it down and generalized it before. So the model, which we're summarizing as M, includes F, which is the probability, the stochastic component, G, which is the functional form, could be linear or not, X are the covariates, the explanatory variables, beta are the effect parameters, and alpha are the ancillary parameters. All those are assumed, and then we can run the model and generate data from the model. So for simplicity, we're going to just drop m. We're going to assume that m is there, so we'll write probability as PR of y, but m, all of the assumptions are implicit. Implicit doesn't mean we can ignore them. We have to pay attention to what they are. The probability of a 1 if the model is flipping a coin is entirely different than the probability of a 1 if you're rolling a die, or the probability of a 1 if a 1 means one candidate wins the election. So you have to absolutely know what the assumptions are, what the model is, and that's, but we're just not going to write it down every single time. All right, so where do you get that function? How do you define the function? Well, we're going to define it with 3 axioms. Now, an axiom is not an assumption. An axiom is just something we take for granted. Okay, so let me explain what that is. There's 3 axioms that define this probability, this function. So first of all, the function PR of something, which I'll call z, is always going to be greater than or equal to 0 for any event or some event z. So it's always going to be greater than or equal to 0. Now, I know you may be thinking, well, wait a second, it can't be greater than 1 because probability is always between 0 and 1. And that's true, but these are the minimal axioms, so we'll get there. Number 2, axiom 2, is the probability of the sample space is 1. So what is the sample space? The sample space is you run the experiment, you flip the coin, you roll the die, you run the election, and the sample space is the collection of all the things that could happen. So the probability that something's going to happen, including nothing if that's one of the possible outcomes, is 1. Okay, so that's everything. If you combine those two, then this function PR can only be between 0 and 1. Okay, there's one other axiom also, and the other axiom is if Z1 through ZK are mutually exclusive events, right? Which means if one happens, the other can't happen. You roll a die, you get a 2, you don't get a 6, right? You can't get a 6. It's impossible to get a 6. You can either get a 2 or you can get a 6. You can't get both. That's mutually exclusive. These are the three axioms that define probability. The third one. If they're mutually exclusive events, then I should say the rule, and the rule is the probability of Z1 and the union of the probability of Z2 and Z3 all the way to ZK is equal to the probabilities of them separately. Okay, so you can just add up the probabilities if they're mutually exclusive events. And so if you want to know if you're rolling a die and there's 6 possible outcomes, each one has the probability of 1/6 of turning up. And if you want to know what's the probability of a 1 and a 2, since they don't overlap, it can only be either a 1 or a 2 or one of the other options. The probability of a 1 or a 2 is the probability of 1, which is 1/6, plus the probability of 2, which is 1/6. And so the probability of a 1/2 is 2/6. Okay, so that's all that's saying. 1 and 2 imply, as I said, that the probability of Z is always between 0 and 1. We could have just said that from the beginning, but there's no reason to be repetitive. The axioms are the simplest possible set of assumptions or criteria or setup that we're going to have to define the function. All right. An important thing is axioms are not assumptions. They can't be wrong. They're just what they are. Okay, now what does that mean exactly? Well, think about it this way. Think about it this way. We just define these things and we find them useful. Remember, they're axioms, so they're a model, right? It's just like saying, wait a second, is the linear model correct or not? Is the stick figure the right model? Well, is it useful? That's really the question, is it useful? So these are axioms, and you might not find them useful, and that's okay. I don't know why, but you might not find them useful. They're certainly not going to be useful for some things, but they're going to be useful for a lot of things. And so I'll show you that they're going to be useful. From these axioms come all the rules of probability theory. There's wings of libraries filled with books on probability theory. You could write your whole dissertation on one small aspect just of probability theory. You could spend your entire career studying probability theory, but all of those things can be derived solely from those three axioms. Right? There's nothing else. There's nothing else in probability aside from those three axioms. Now, of course, there's tremendous creativity and work and all kinds of implications that are drawn out of those. But remarkably, it all comes from those axioms. So here's a quiz just to make sure that you understand what we're talking about. Let's suppose we change the axioms. Right? Remember, I said they can't be wrong, but that doesn't mean we can't change them. We could change them. Let's make the second axiom, the probability of the sample space equaling 2. Now just think to yourself for a minute, what happens to probability if we do that? Right? We need a little music. What happens if we do that? If we change the probability, the second axiom of probability to the probability of something happening being 2? Do you know? Well, what actually happens is that the probability doesn't range between 0 and 1 anymore. It ranges between 0 and 2. And then we would say, that's really likely. That has a probability of like 1.75, right? And that wouldn't be wrong. It would just be, a different definition for how we're defining probability. And so that's the sense in which an axiom can't be wrong. Like, so what? It goes from 0 to 2 rather than 0 to 1. It just doesn't really matter. So that's what it is. Those are the axioms. We can apply these rules, and in the literature they apply these rules analytically, which is a synonym for mathematically, through derivation, or via simulation. As I said, we're going to find simulation a lot easier, but sometimes we'll do it analytically because it may be faster, it may give us intuition, may help our computers run faster. But we're certainly going to run it by simulation to check the analytics, although we may run the analytics to check the simulation. Okay. All right. An important way to represent a particular type of probabilities are probability densities. Okay, so here's an example of some probability densities. Probability densities are defined for any outcome of the experiment. They tell us the probability that something's going to happen. Okay, they assign a probability to every possible y or to every possible range of y. The difference is important. A function, which is not PR of y, but what it's sometimes written as big P of y, sometimes little p of y, sometimes, as I have done in the past in these talks, f of y, such that, and I'll just use p of y for now because we'll remember it as probability, but we'll understand that it's not the same thing as the probability function PR. So this p of y, which means the probability density, it's always going to be greater than or equal to 0 for any y. For discrete y's, they're going to sum up to 1. So if we have the probability of a 1 if we flip a coin, and the probability probability of a heads if we flip a coin, and the probability of tails if we flip a coin. If it's a fair coin, they're both 0.5. If it's an unfair coin, it might go like this. But either way, each of those probabilities is going to be greater than 0, and the sum of those two probabilities, heads or tails, is going to be 1. Okay. Now, I've just excluded the possibility that you flip the coin and it lands on its side and it stays there, or you flip the coin and somebody catches it, or you flip the coin and like the world explodes. But that's a model. That's the whole idea. But these are the two rules that define all probability functions when they're discrete. If they're continuous, then we don't have the rule that the sum of the heights is equal to 1, because there's sort of an infinite number of them, so it doesn't really make sense. So instead what we'll say is the area under the curve is equal to 1. So you see that, so we're going to write that down. So how do you write down the area under the curve? Well, some people will recognize this as a way to do that, right? So there's, that's an integral. But let's go up here and look at these things. So this is a discrete probability distribution. You don't know the name of it. It's just a discrete probability distribution. The horizontal axis here, it's written as x, but we could think of it as y. I can take the values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Can't take any other values if this represents the whole thing. Each one of these is above 0. And the sum of these, if you add them up, had beta equal 1, right? Because that's what this says here. Okay. And so if we ask ourselves, are these curves PDFs? That's the way to understand whether you understand probability density functions. You just look at these two and ask whether they're PDFs. So for the discrete one, it's relatively easy, right? You can literally add these numbers, right? This is 0.02, this is 0.04, right? You add them all up. And you just see, do you get 1? And you make sure that each one of them can't be negative, right? They could be 0, they could be positive, but they can't be negative. And so, if those two rules apply, then this is a correct, it fits the definition of a probability density. It fits the definition of a probability density, in this case, for a discrete density. Sometimes that's called a probability mass function rather than a probability density function. We'll just use probability density for both. Now, over here's a normal distribution looking like thing. If you look close at these numbers, the vertical axis is going to go up above 1, which is interesting. The horizontal axis is again going to be y. And here's my question. Okay, so first let's look at this. Does this thing sum to 1? Okay, what is the area, well, you can't sum it. It doesn't sum like these guys, but we want to know if the area under this sums to 1. So how do you do that? Okay, well, you have to figure out, does the area sum to 1? Well, how are we going to do that? Well, the way you do it is with a little bit of math, and so here's how the math works. So you take this curve, right? And you're going to scoop up all the area under this curve. Now, how do you scoop it up, right? Well, you got to start somewhere, go somewhere else, and scoop it up, right? So we're going to scoop it from negative infinity to positive infinity. So see this thing? That stands for S. So that's a big S for scoop. And the scoop goes from negative infinity to positive infinity. That's why there's a negative infinity there, and there's a positive infinity there. What are we going to scoop? We're going to scoop f of y. Okay, and then which direction are we going to go? Are we going to scoop up? Are we going to scoop out of the page? Are we going to go scoop on a different dimension? No. We're going to do the scooping over y. So that's with the D. D stands for do, and we do it over y. Okay, so I hope you understand that lying is a really good teaching tool. Okay. In any event, I'm making this up, right? In any event, this is an integral. This is the integral for the area under the curve f of y. And the question is the area under this curve 1? So how can you do it by looking at it? Well, you could put over this a rectangle that takes in too little in the middle and too much over here. And then you could multiply one by the other and see whether you get about 1. So that's how you could do it by the eye. Here's one that's really wacky. Nothing wrong with it. It perfectly fits. It is a probability density. But it goes up here. If you look closely at the vertical axis here, 1, 2, 3, 4, 5, 6, right? It goes all the way up to 6. Sorry, I can't see it very clearly. But the height of these bars, the height of these curves are not probabilities. The area under the curve has to be 1. That's the only thing that's necessary for a continuous probability distribution. Okay, so if you did the integral, you would find that the area under each of these separately is actually 1. Okay, so we just have to get used to the fact that there's a different representation for the continuous one than the discrete one. Let's think about then how to get from a probability density to that function that I showed you a couple of pages ago, PR. Okay, so how do you get probabilities from the probability density? Okay, all right. So we're going to have a discrete on the left side and a continuous on the right side, and we have examples of both up at the top. And now I'm going to show you the equation. We want to know, let's suppose, what's the probability that y is between two values that I give you, a and b. What's the probability that y is between a and b? Well, if it's discrete, it's really easy. I already did that with the example that I told you a little while ago for rolling the die. There's a discrete probability density, so you just add them up. You just add up the p of y's, you add up the heights of the curves for each of the values, for each of the bars between a and b. And so here's an example here where a and b, maybe a is, I guess, here, and b is all the way out here. And so you just add up all the red bars, the heights of all the red bars, and that's what you get. So you get the sum for when y is between a and b of p of y, which is, in the discrete case, the height of the curve. So that's really easy. This d of y here, I should probably delete that. It's okay to leave it there, but but in any event, I think I would probably just simplify it by deleting it next time. In the continuous case, what do? Well, you actually have to take the integral. You scoop from a to b over the dimension y. And here's an example from minus 9.8 to 1.4. And you scoop from one to the other, right? You scoop from there to there. And you just figure out the area under the curve here. And that area, as a function of the total area, is the probability that y is between a and b. In this case, between minus 9.8 and 0.14. Okay, so that's exactly how you do it in each case. All right, now one weirdness about this is, what's the probability that y takes on a specific value, which I'll call little y? Okay, how do you actually do that? What would that be? Well, in the discrete case, it's very easy. It's just the height of the curve. In the other case, what's the probability that y takes on a specific value? And the answer is 0. Well, wait a second. Well, 0 feels a little weird because it's 0 for any value. So that means the probability that for a legitimate probability distribution, let's say a normal distribution, the probability that y takes on any specific value is actually 0, which is totally weird, right? Because clearly something's going to happen when you run the experiment, but it says the probability of anything is 0. So 0, it turns out, is not exactly the same thing as it's not going to happen. Well, that's weird, okay? So why does this happen? This is the quiz. Like, why is this, right? Well, it's a model. You can ask yourself this, and it's a good, when you see a little y in my slides and my talks, to hit pause and just think to yourself, what could this be? What could the answer be? Because if you can think of it yourself, you'll do much better than if I just tell you. Okay, so in any event, I'm encouraging you to pause. But what's the answer? So the answer is that the probability density is just a way of getting to the probability. It's not the probability itself. And this turns out to be a useful model, a useful way of getting there. Okay, so for a discrete case, we can actually use PR in the definition of the discrete probability density. In the continuous case, we just come up with this new thing. It's called a PDF. It's just a discrete. It's just a continuous thing, and we define probabilities based upon intervals. Now, you'd say, well, why don't you just define them based upon the heights, and then it'll be as easy and simple and straightforward as the discrete case. Well, the reason you can't do it is because what would the probability be that you would assign? Okay, so if you assign some teeny itsy bitsy value to this exact value, how many exact values are there? Well, it's a continuous variable. If it's a continuous variable, there's an infinite number of values. So what that means is, no matter how small a value you assign to each of those points, as long as it's not 0, when you add them up, if you do it in a discrete way, there's an infinite number of them, so it adds up to infinity. It doesn't add up to 1. And remember, 1 is the goal, right? The area under the curve has to be 1 in order for this to be a PDF. So they have to be 0, okay? So that's actually the way it is. Now, you don't like that? It's okay. This is just a model. You can come up with another model. This one seems to work. It seems to be useful, so we're going to use it. All right, so what should you know about every PDF when you're going to use it? You don't have to derive it yourself. You don't have to do a lot of things, but you have to know some things about it. First thing is you have to know the assignment of a probability or probability density to every conceivable value of y. You have to know that because that's what the PDF is. That's what it does. That's what it's going to do for us. That's how we will use it. You have to know the first principles. That is the substantive assumptions from which you can derive it is possible to derive the actual functional form. The actual functional form, the actual probability density, the final formula, the final expression is something we'll use. We'll have to understand how to use it. And you can get from the first principles down to the final expression by mathematical calculation. And you may be interested in doing that, and you may have done that for some simple cases. We may do it in this class for some very simple cases. But it's okay with me if you don't actually do the whole derivation. I don't think you really need it. I often don't go through the whole thing. I trust the literature when they say that the binomial distribution was calculated correctly, although that one it's easy to see. You can go through it. It's actually illuminating. But the minimal stuff that I really want you to understand is the assignment of probability or probability density to every value of y, the first principles, which connects this mathematical model to the substantive world. Those are the assumptions, like there's independence or mutual exclusivity, as we talked about a minute ago. You have to know those things because otherwise, what is it that we're doing? And finally, it's how to use the final expression. I'd also like you to know how to simulate from the density, from the probability density, because then we can make it useful. I'd like you to know how to compute features of the density, such as its moments, both analytically, at least in principle, and sometimes actually analytically, and by simulation. you should also understand how to verify that the final expression is actually a probability density, a proper probability density. The verification, of course, is for every value of y that you put in, is the probability never negative, and does the area under the curve sum to 1. Okay, so let's go through a small number of very simple cases so that we can completely understand the probability densities. We're only going to do some simple cases, some that we'll use later on, and that will give us enough intuition so that when we're introducing a new statistical method that relies upon a different probability density, you'll say, oh yeah, it's a probability density. And I'll say, you've never seen this probability density before, and you should think to yourself, oh, okay, but it's just the probability density, so tell me what the first principles are. Yeah, we can go back here. Tell me what the first principles are, how it connects to the substantive problem at hand, whether that's really right, how does it work, how do we assign the probability or probability density to all the conceivable value of y's and y, and each of these other things. Okay, so a simple first one is the uniform density on the interval from 0 to 1. Here's a picture of it. Y can take on any value from 0 to 1. That's the horizontal axis there. The vertical axis is the probability density. Actually, this should not be PR. This should be P, not PR. Because the probability of any one of these values is 0, but the probability density is always going to be 1. Okay. So from this, we have first principles. What are the first principles about the process that generates y of I? Well, y has to fall within the unit interval. Okay, so y has to be between 0 and 1. So the integral, the area under this curve is 1. You can see this integral is easy to calculate here, because what's the area here? Well, it's this length, which is 1, times this length, which is 1, and 1 times 1 is 1, and so this integral is 1. Isn't that great? Secondly, it's this long mathematical thing, but it's really very simple. The idea is that the probability of falling in an interval a and b is equal to the probability of falling in an interval c and d, as long as the interval a and b and c and d are the same length. Okay, so that's the whole thing. Those are the two densities. This is not a particularly interesting probability density. It doesn't apply to a lot of things in the real world, but it's a basic building block on which we will build other densities. How do you know it's a PDF? Again, that purple area is always above 0, and the area itself is 1. Then it's a PDF. Okay. How do you simulate from it? Right? How do you simulate from this density? Well, we need random numbers between 0 and 1. Well, in R, it's just RUNIF, which is random uniform. And if you put 1,000 in there, you'll get 1,000 random numbers. That's it. Okay, that's how I want you to know. And we'll talk about how R produces those random numbers in a little bit. This PDF has no parameters, so there's nothing to estimate if we were going and doing inference, but we could add some. Could we? What would it be like? Well, we could say that y doesn't go between 0 and 1. Let's say it goes between 0 and pi, and we don't know what pi is. And we could try to estimate what pi is on the basis of the data, and that would be an interesting problem. Maybe not that interesting, but we could do it, right? We could take the maximum value in the data, and that would be our estimate of what that value is. It's not a particularly good estimate, right? Because the truth could always be larger than it, so the maximum value in the data is always less than or equal to the true maximum. But anyway, that's an interesting statistical problem. That's a way of adding a parameter here. Okay. Now let's go to an actually even simpler probability density because it's discrete, and it's one that we will actually use. It's the Bernoulli probability density. By the way, Bernoulli, you hear Bernoulli a lot. I've already given you this example. Bernoulli comes up in math all the time, and you think, well, who was this guy Bernoulli? Because there's so many things named after him. Actually, Bernoulli is a whole family of people, all with the last name Bernoulli. There's like 11 or 12 of them, and so they did a lot of things. Okay, so here's some examples again of the Bernoulli distribution. The outcome can either be 0 or 1. If one is high, the other's low. They sum up to 1, so you push one down, the other goes up, right? It's got to be like that. Each of the bars are always above 0, so it sort of fits. The first principles about the process that generates y in a Bernoulli, what are they? Okay. They are, first, y has two mutually exclusive outcomes. So if you're using this to model the outcome of the presidential election, your assumption is that either Biden or Trump can win. Okay, and no one else can win. It's impossible for anyone else to win. It's impossible for both of them to die and the vice presidents to be appointed as the candidates and something else can happen. It's impossible, zero probability, like it can't ever happen. Okay, well, it's a model, right? Second is, so the two outcomes are mutually exclusive and exhaustive. I just gave you the example of exhaustive. Mutually exclusive means it's impossible that they could both be elected, right, because there's no overlap. Okay. So what's an example that violates these rules? I just gave you examples that violates these rules. Don't ask me that. All right. In this simple case, I'm now going to go through and compute some features of this probability density analytically, and then we'll also do it by simulation. I'm going to do it in this simple case because we can see what it is. We can understand the answers. We can do it all. And that will give us intuition for more complicated cases where we won't bother to do the full analytics, but we'll just use the result that someone else calculated, or we will do it by simulation ourselves. Okay. Okay, so the mathematical expression for this probability density function, or probability mass function, PMF, as it's called sometimes, looks like this. So the probability that y takes on the value 1 given pi, I have little i's to be reminiscent of the fact that we're going to have data eventually, and an I is observation I. So the probability that y takes on the value 1 is going to be pi. So pi of I is the height of the bar referring to the 1. And the probability that y is 0 is 1 minus pi. It's given the model, so I have the m in there, right? The model part, the key piece of the model, which is the pi. So I'm assuming the parameter itself is known. If the parameter itself is known, the probability of the height of the bar for the probability of y equal 1 is pi, and probability y equals 0 is 1 minus pi. They sum up to 1. The parameter pi happens to be interpretable as a probability. So it is a parameter. That's our parameter. We could think about estimating it, but right now we're talking about probability, so we're going to assume it. We're going to choose it basically. We can put these two things together in one formula for convenience. So this is the Bernoulli probability density, the mathematical form of it. The probability that y is equal to some value, little y, given pi, is equal to pi to the y times 1 minus pi to the 1 minus y, if y is equal to a 0 or 1 and 0 otherwise. So I don't have that written down here, but that's implied. Now, what is that formula? So let's just think about it, make sure we understand it. We have pi to the y. So let's suppose y is 1. So if y is 1, what happens? So anything to the 1 is itself. So pi to the 1 is pi. 1 minus pi to the 1 minus 1, anything to the 0 becomes 1. So if y is 1, this whole expression becomes pi. And if y is 0, this expression becomes 1 minus pi. So this expression just reduces to these two. So that means it's just a simple way of writing down those two, or it's a single unified way of writing those two. You'll see alternative notations for that same probability. Sometimes we'll write it as Bernoulli of y given pi, sometimes f of b of y given pi, sometimes BERN of y given pi. Don't get hung up on the particular notation. People don't have to use your notation, and unfortunately they won't usually. But you just have to understand exactly what it is they mean. All right, so let's come up with the features of the Bernoulli analytically. First, the expected value. The expected value of y is, by definition, not just in the Bernoulli, but always, the expected value, the mean of the distribution, the number that we expect to get on average, is equal to the sum over all y of y times the probability of y. Okay, so in this case, it's equal to 0 times the probability of 0 plus a 1 times the probability of a 1. Now, it's 0 times the probability of 0, so that first term just goes away, but that's the way that you actually calculate it. And a 1 times the probability of 1, the 1 obviously goes away, so what's left is the probability of 1, which is pi. So the expected value is pi. So you're flipping coins that may be, that is fair with, you're flipping coins where the probability of a 1 is a pi. What do you expect to get on average? You expect to get pi. So if it's a fair coin, on average you expect to get 0.5. Right? If sometimes you get 1, sometimes you get 0. Okay, what's the variance of a Bernoulli? The variance of a Bernoulli, first we'll use the official definition of a variance. The variance is the expected value of the deviation, it's the expected value of the squared deviation between y and its expected value. It's easier to write down by little derivation. The variance is equal to the expected value of y squared minus the expected value of y quantity squared. Okay, and so all we need to do is calculate each of those things. The second one we already know. The expected value of y is pi. It's at the top of the page. And we're interested in the expected value of y squared, so we just square it. And all we have to figure out now is the green expected value of y. How are we going to do that? Where are we going to get that from? We're going to have to figure out how to do that. Okay, because I've given you the rule for the expected value, and now we have a variance except for this one thing. So how do you figure out the expected value of y squared? Okay, how do we compute that? All right, so it turns out to be a special case of the expected value of functions of random variables. So we'll always have to know how to compute the expected value of functions of random variables. Some function is g. Now I'm reusing this g. Previously I used it as the functional form in a statistical model, but here it's just some function. So it could be the square root function, could be the squared function, could be an absolute value, whatever it is. It's some function, and it then is where are we here? It then is equal to so the expected value of some function is equal to the sum over all y, g of y times the probability of y. Okay, so in the special case of this, where we're just interested in the expected value of y, the function is just the identity. So the expected value of y is equal to the sum over all y times the probability of y. But it turns out it generalizes in this nice, convenient way. If it's continuous, there's a continuous version of it. It's basically the same thing, but we just take the integral instead of the summation. So, for example, the thing that we actually set out to find is the special case of this, which is the expected value of y squared. So the squared is the function g of y. And how do we do that? Well, it's the sum over all y of g of y, which in this case is y squared, times p of y. Okay, so what do we do there? Well, it's 0 squared times the probability of 0 plus 1 squared times the probability of 1, which also simplifies very nicely. 0 squared is 0, 1 squared is 1. The whole thing becomes, so the expected value of y squared is equal to the expected value of y, which is equal to pi in this case. So I'm going to come back and I'm going to put these together in a second, but let's just look at this because this is a very useful thing. This will be more useful than just to calculate the squared term. It will be useful to calculate the expected value of any function, not only the squared term. So we'll see it a lot. We should come to terms with it. And the cool thing about it is it's not just a rule that you have to memorize, but the cool thing about it is you don't have to figure out first the probability density of g of y. So you could have done this by you're given the probability density of y, that's p of y, and then what we could have done is figured out from that how to get the probability density of g of y, and then follow the rule for the expected value of y. But that would have been hard, and this is a trick, so it's easier. Okay. All right, so now we're going to use the above results. We're going to put them together. That's the definition. That's the easier version. We now know what each of the parts are. So the variance of y is equal to pi minus pi squared. Put them together. It's pi times 1 minus pi. This makes sense. We have this little beautiful handwritten graph here that I drew. The mean, the expected value, pi, is along the horizontal axis, can only go between 0 and 1. And the vertical axis is the variance, which is pi times 1 minus pi. And so if pi is 0, well, 0 times 1 minus 0 is 0. If pi is 1, then 1 times 1 minus 1 is also 0. So that's why the ends of these things are 0. And the largest possible variance in a Bernoulli is at 0.5. Now, this makes sense, right? If you're flipping coins and you want the largest possible variance in the outcomes of the zeros and ones, do you want a fair coin or do you want a biased coin? Turns out you want an absolutely fair coin. So that's how you get the biggest variance between the zeros and ones. Any bias is going to wind up with more zeros than ones or more ones than zeros, and that's going to reduce the variance. Okay. These are very simple examples, but the intuition generalizes in quite a big way. Okay, so how do we simulate from the Bernoulli with parameter pi? Again, we're going to do this with every probability distribution, but in different ways. So we'll take one draw of u, we'll just call it u, from a uniform density on the interval from 0 to 1. We're going to set pi to a particular value. And then, remember the first line there, to get u from a uniform density, we already know how to do that. That's RUNIF and R. Okay? So where are we going to get the 0 and 1 draws? We're going to use that to get there. So we're going to set pi to some particular value. We have to set pi because otherwise we don't know what the probability density is until we choose the parameter values. We're then going to take a random, then our random draw is going to be a 1. It says set y equal 1. If u is less than pi, and we're going to set it to 0 otherwise. So basically, we already know how to draw numbers between 0 and 1 somewhere continuously in there. And then if you want to turn that into zeros and ones, you just have to know what pi is. If pi is 0.25, then you assign this piece to the 1 and this piece to the 0. So that's how you do it. So here's in R, very simple code. Here's 1,000 simulations. We create our Bernoulli pi equal 0.2. I might have liked to use pi here, right? Pi, right? But pi is not a good thing to use there because pi actually has a meaning already, 3.1415, whatever it is. That number, you can't reuse that, so we're going to use just a different symbol here. Let's suppose we set it to 0.2. Then we have our RUNIF. We're going to get sims of them, which will be 1,000 of them, put them in there. And then if u is less than Bernoulli pi, we turn them into integers, we print the results, and we get lots of zeros and ones, etc. Okay, so that's how you get Bernoulli simulations. What can you do with the simulations? Think to yourself what you can do with these simulations. I mean, it's not particularly exciting. It's pretty straightforward because you already understand the Bernoulli analytically completely, so the simulations seem superfluous, but actually they can be useful. They can be useful in more sophisticated cases. So if we wanted to plot the probability density and we didn't know how to do it, we could simulate from it and we could just plot the proportion of ones and the proportion of zeros. If we wanted to get the expected value of the Bernoulli, but we didn't know how to do it analytically, we could take random samples given some pi, and then we could calculate the proportion of ones. We could basically just average the results. That would give us an estimate of the expected value. We could get the variance by simulating, calculating the sample variance. That would be our estimate of the variance. We can calculate anything else we like. Okay, so that's the Bernoulli. Let's go to another distribution. We're only going to do a couple more. This is the binomial distribution. So the first principles of this distribution differ from the Bernoulli, but it builds on the Bernoulli. So the idea of the binomial distribution is we're going to have NIID, which is lingo for independent and identically distributed. So they're independent, which means they're unrelated, and identically distributed, which means they have the same Bernoulli distribution, same distribution, but in this case Bernoulli. So there's N, capital N, not number of observations, so different than number of observations, which I've been using little n for. NIID Bernoulli trials, so we're going to write that down as Y1 through Yn. Each one is a Bernoulli outcome. That's called a Bernoulli trial often. The trials are independent. The trials are identically distributed. Identically distributed means they are Bernoulli. They have the same first principles as Bernoulli, and they have the same pi. So we're going to observe not the results of the Bernoulli trials. We're going to observe instead the sum of them. So we sum them up. So the density or the probability mass function looks like this. This is the formula for the Bernoulli. My guess is you've seen this before. Let's look at the pieces, okay? The blue is n choose y. It's the number of little y's that you can pull out of big N. And that's there because 1, 0, 1, if there's three possibilities and you ran the 3 Bernoulli trials and you got those 3 numbers. That's the same from the perspective of a Bernoulli as 1, 1, 0. It's the same because all we're doing and reporting is the sum. So it's the same thing. Both are y equal 2. Pi to the y, that's the red piece in the formula, is there because there's y successes. What's a success? Well, it could be electing a candidate of a particular party. It could be flipping a coin and getting a heads. It could be flipping a coin and getting a zeros. We just have to call it something. So in the literature, they usually call it successes. So it's y successes with pi probability each. And why do we get to multiply them together? Like, because it's pi to the y. Why do we get to multiply them together? Because independence allows you to do that. If you know the probability of A and you know the probability of B and you're interested in the probability of A and B and you know that A and B occur independently, then you can multiply them. The probability of A and B is equal to the probability of A times the probability of B. Similarly, 1 minus pi to the n minus y is there because there's n minus 1 failures, or the election of the other party, let's say, with 1 minus pi probability of each. Okay. The moments of a distribution, that's some more lingo. That means the mean, the variance, and other features of the distribution, specific features, skewness, kurtosis, etc. So the mean of this distribution is the expected value of y, same notation, is equal to n times pi. So that's the expected number of events. Right? N is the total number of trials. So the possibilities, it goes from 0, 1, 2, 3, all the way up to capital N. It can't be anything else. It can only be in there. And the expected result, the expected number of ones, the expected number of successes, is n times pi. And the variance is pi times 1 minus pi over n. So these make sense because it was built on the Bernoulli distribution. Basically, it's the Bernoulli results, but times n for the mean and divided n by the variance, for the variance. Okay, how do you simulate from the binomial distribution? Remember, we simulated from the Bernoulli by simulating from the uniform and translating those into Bernoulli. Now we're going to simulate from the binomial by simulating from the Bernoulli, which we simulated from the uniform. See, here's how it works. To simulate from the binomial, I changed notation just to keep you understanding and focused on the concept rather than on the notation. We're going to simulate n independent Bernoulli trials, each with parameter pi. We're going to add them up, and then we got it. Okay, that's the whole thing. So it's quite simple because we already know how to do each of the pieces. What can you do with the simulations? Well, now it's a little more interesting. Suppose you wanted to know, or were given the task of trying to figure out what's the probability of at least 4. So, or if you use this to model something like the number of days in the last week that you read the newspaper, and you want to calculate the probability of having read the newspaper at least 3 of the 7 days, you could calculate that by taking random draws and just calling it a success if it was at least 3, and a failure if not, and then just averaging and calculating the fraction of ones, calculating of those successes, and then we have that probability estimated. Okay. Let's pause here because at the beginning of this chain, right, to get the binomial, we use the Bernoulli. To get the Bernoulli, we use the uniform. To get the uniform, we used RNIF. Where the heck did that come from? Where do you get uniform random numbers from? Okay, here's the weird thing. Random is not haphazard. Random is not haphazard. You can't just make up, numbers. Like if you're asked to make up numbers between 0 and 1 randomly, well, first of all, you have to ask the question. Randomly that's not a definition, right? Randomly is random draws from some probability distribution. You have to know what the probability distribution is. If it's uniform, that's fine. Then my question is, how do you get it from the uniform distribution? How do you randomly draw from the uniform distribution? Well, random is not haphazard, okay? And so we're going to have to do this in some particular way. In fact, there's a great class experiment where you have everybody in the class make up random numbers, just from 0 to 1 or zeros or strings of zeros and ones without actually flipping coins or whatever it is. And they just write them down, okay? And then you have some of the people secretly actually create random numbers by some physical mechanism like flipping coins. And then the numbers get sent up to the instructor, and the instructor figures out who made up the numbers and who actually used the physical mechanism to create the random numbers. It's not that hard because humans tend not to create actually random numbers when given the chance. In fact, this is used to detect fraud in elections. It's used to detect fraud in accounting numbers in corporate fraud and other things. And this comes from an observation called Benford's law, which is really cool. Let me explain to you what this is. Okay, so if you take a whole bunch of tables, like let's suppose you're watching a seminar and you're really bored with the paper, okay, and you have the paper in front of you and it's an empirical paper, and there's a whole bunch of tables in the paper. Some of them are population numbers, some of them are regression coefficients, there's standard errors, there's all kinds of different things. That's the first principles of what I'm about to tell you. You take all those and then you're bored, right? So you're sitting at this table and you write down 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. Okay, and then you go through all the tables and you take the first decimal point, the first number after the decimal point in all the tables. Now that's utterly arbitrary because you could present the numbers times 100 or whatever it is. It was totally the choice of the author. But you take them all and you combine all the tables and you just tally them up. Now, you'd expect them, I think we would normally expect them to be, sort of uniform, right? Not true. Not true. If you try it, and Benford's law holds, then what will happen is there'll be more 0.1s than 0.2s, than 0.3s, 0.4s, 0.5s, 0.6, all the way on up, which is totally weird, right? Totally unexpected, but it's actually true. I've done it myself. You should try it. It's really cool. And so and it turns out if you, Benford proved, and others Benford found, but others have proven, following up from this, that if you combine like all possible probability distributions, it turns out you don't get the uniform distribution, you get something more like this. Something closer to exponential. So there's more 0.1s in the world than there are 0.2s, than 0.3s, all the way up to 0.9s, which is totally crazy. And so what that means is you can take election statistics, which really should be random, and and if they really should be random, then they really should look like this, right? But if they look like this, then probably somebody was making up the numbers. Not necessarily, because people are allowed to vote any way they want to vote. But it could be the case. It's potentially indicative, and so it is actually used for that. Okay, so you can't make them up. So where do you get these things? Well, you get them from random number generators. But wait a second, random number generators are perfectly predictable. What? What does that mean? Well, what that means is that they're mathematical formulas. They're pseudo-random number generators, to be very precise. And they're generated so that the digits occur with 1/10 probability, right? It's because there's 10 of them. There's no time series patterns from one number to the next number, etc. However, they are deterministic functions. Your computer is entirely deterministic. It is true that sometimes it feels like you do the same thing twice, and one time it works and the other time it doesn't, but that's not the case. It's a deterministic machine. Every time you do the same thing, you should get exactly the same answer given the same initial state. So what a pseudo-random number generator is, which is the thing inside your computer, it's a mathematical formula. It's a recursive mathematical formula where you give it a random seed, that's the starting point, and then it calculates the next number. And those next numbers, if you know the pseudo-random number generator and you know the seed, are perfectly predictable. Every number subsequently will be exactly what you expect it to be. In fact, if you use the same seed and run the thing twice, you're going to get exactly the same sequence of numbers, which is very useful for replication purposes. We often do that. I once bought a computer, And it looked fine, everything was fine, and I brought it back to the store and I said, this computer doesn't work, and they checked it out and they said, it works, you're not getting your money back. I said, the random numbers don't make any sense, they really are wrong. And they said, what are you talking about? I mean, what are random, like they're random, you know? And I said, no, they're not random. And I showed them they're not random. But I had to actually give them this lecture, basically, which was really insane. But in any event, I got my money back. So how do you create real random numbers? There have been efforts to do this. People remember those lava lamps, right, with bloomp, bloomp, right, wax and stuff, and it heats up. Well, we know from physical principles of, of physics that there's turbulence in there, and so they take a video camera on the lava lamp and digitize the thing and take the zeros and ones, whether there's wax or water. There's a variety of other clever ways of doing this. For our purposes, we probably don't need it, but it's important that you remember this slide, because there will be a time 5 years from now where you're running 10 billion simulations, and for some reason, every 53rd one is the same or something weird, right? You'll remember this and you'll say, wait a second, maybe it's the random number generator. And then you can switch the random number generator and fix the problem. That doesn't come up very often, but it does come up sometimes. Okay, so we need to draw random numbers. So I'm going to give you some way of taking random draws from arbitrary probability distributions. We already know how to do it for the uniform because there's RU and IF, and we have a sense of how it's actually being done now. But suppose there's an arbitrary probability distribution. Suppose there's the purple one on the left here. Right? Like what would that look, like how would you draw from that? Like there's no formula, there's nothing in R to do it. So it turns out there's some ways, and we're going to use two ways. One is discretization and the other is the inverse CDF method, and we can also combine these. So turns out there's a whole literature on how to draw random numbers. The literature on Markov chain Monte Carlo methods, which is a very important advance in statistics in the last several decades, enables you to draw all kinds of draw random numbers from all kinds of probability distributions. It's a very important innovation, but I want to give you a feel for one somewhat simpler way of doing this. So we take that purple probability distribution, which is all quite it's got these bumps in it. It's not any particular known probability distribution. And so how do we do it, right? You may wind up in this case. What are you supposed to do? Well, if it's univariate and it looks like that, here's what we do. We divide the PD up into a grid, like we just discretize it. We approximate the probabilities with trapezoids, right? Remember, trapezoid is straight lines, and then a tilted roof, right? And that's what I have drawn there. So the purple is the probability distribution, and the lines are the trapezoids. Okay, so now we have these areas under the trapezoids. We map the 0-1 uniform draws to the proportion of the area in each of the trapezoids relative to the whole gigantic polygon, basically. Okay, and then take random draws. So we randomly choose a polygon. Once we have a polygon, and then we return the midpoint of each trapezoid. Now it gets there. It's not perfect, of course, because within within one of those trapezoids, we're only going to get one number, just the midpoint. We're not going to get any number. But the cool thing is, you can just write this when you write the code. You just say, well, how many trapezoids should there be? Instead of saying 6, just say k, and then increase k to a very large number, and it makes the approximation better and better and better and better. And so that's one way of doing it. This works for a few dimensions. It's infeasible if you have 20 variables, but it gives you one way of doing it. Let me give you one other way. This is the inverse CDF method. Another way of drawing arbitrary continuous PDFs. Okay, from the PDF, compute the CDF, the cumulative probability density. Okay, so what is the cumulative probability density? Well, it's the integral from negative infinity up to y of this function dy. So it tells you the cumulative density function always tells you the probability that y is less than or equal to some value y. So this f of y is the probability that y is less than or equal to little y. That's what it always is. Okay. So first we calculate that. You have to do it analytically. Second is we define the inverse CDF, okay, to go backwards. Okay, now let's just see what that is. Here's an example of the CDF. So for every y, the CDF is here. So for this value of y, right here, then the height of the CDF is the probability that y takes on a value at least this large. I don't have drawn here the original probability density and then the accumulation of it. You may have seen, there's a normal distribution. The cumulative normal distribution looks sort of like an escalator, right? Like the logit curve, basically. In fact, it's a probit curve, but that's the same thing. Okay, so what we're going to do is instead of have this as the CDF, we're going to go backwards. We're going to start at this vertical axis and we're going to go down to y. This is the inverse of the function, and the inverse of f inverse of f is equal to y. That's the definition of the inverse. Okay, so here's how it works. We draw a random number u, then f inverse of u gives a random draw from the probability. Let's just look here. Okay, so once we have the CDF of y, remember the only thing we had to do here that was hard was calculate the CDF. And often you can get that, it's just given somewhere, but you might have to calculate it. If you can calculate it, then you get a graph like this. Then what you do is you take random draws from the uniform, that is UNIF, and you stick them in here. You stick them in on the vertical axis, you go over to the point on the horizontal axis that it corresponds to, and then that's your random draw. So if you randomly draw down here, then you pull out a y here. If you randomly draw all the way up here, then you pull out this y. And that's the whole thing. Turns out you can then combine the two methods. You can create a refined discretization method. You can choose an interval randomly as before, based on the area of the trapezoids. You can draw a number within each trapezoid by the inverse CDF method applied to the trapezoidal approximation. And then that's even better. Drawing random numbers from arbitrary multivariate densities, you have to go to this other literature that I mentioned because there's a lot of work there. It has made things possible to do that we thought would take centuries of developments in computer technology, right? Because you could just calculate things directly. If you don't know how to do simulation, you can approximate them or whatever. Well, it turned out that the advances in Markov chain Monte Carlo methods, which were used to draw, mostly used to just draw random numbers, enables us to do things that we just thought would either never have been possible or would have taken centuries. And actually, they've been really terrific progress. Okay, all right. Normal distribution. Now I'm going to do a multivariate normal distribution. So you've seen the normal distribution, you've heard of it, you've coexisted with it at least. So there's many different first principles that arise to give them, which lead to the normal distribution. A common one is the central limit theorem. So if you have the means of some data with n observations, and you take all those means and you plot them in a histogram, and then you do the same thing again with n observations, but n is larger, and you do it again with n observations, but n is even larger. That distribution of the means will tend to the normal distribution. That's a very intuitive, qualitative sense of the first principles. We will do more specific ones later. So the univariate normal density with mean mu and variance sigma squared, color-coded so you can see it in the formula, look like that. The first time you see this formula, you think, I don't really know why anything is in that particular place. That's totally fine. But if you just keep looking at it, every time we show it to you, you'll at least remember that you saw it before, and you'll say, oh yeah, I know what that is. You still don't know it any better, but that's okay. It is what it is. Right there, and it will be useful. So it's like a model. In fact, it is a model. It's the normal model. Okay, so that's the univariate normal distribution with two parameters, the mean and the variance. You know what they look like, right? It's going to look like this bell-shaped curve. The mean is going to move it around. The variance is going to make it have smaller variance. Sigma squared is going to make it have smaller variance. It's not ever going to be bimodal. It's never going to be discrete. It's never going to have a little bump over here. It's never going to be skewed. It's just the normal, okay? It has the mean and the variance. Okay, I'm going to build on this. We're going to use this a lot. And so for simplicity, I'm going to define the stylized normal. So I'm going to call it the stylized normal, which is just the normal with sigma squared set to 1. So that way we only have to worry about one parameter instead of two. So that'll be the stylized normal. We'll use that. And that's what it looks like. It's the same thing as the equation up here, except sigma squared is set to 1, so we have a 1 over there. That's it. Then there's also the standardized normal, and the standardized normal is commonly used in the literature, and it has no parameters. And there's no parameters because the mean is set to 0 and the variance is set to 1. So there's nothing to estimate left, and it's just the standardized normal. It's useful. It used to be used. It used to be very useful because we didn't have computers, right? And there were only tables in the backs of books to look up distributions, and it was going to be unwieldy to have the univariate normal in the back of the book because we'd have to have the normal for different means and variances. And so we translated everything to standard normal, and the only thing in the back of the book was the standard normal. Okay, that's mostly why the standard normal is there. It just makes things simpler. Anyway, we'll often use the stylized normal. That's what the thing looks like. It looks a little simpler. Basically, we just set sigma squared to 1 and mu to 0. All right. Let's remember the regression notation that we had before. So this is the standard version, y equal x beta plus epsilon. Epsilon's normally distributed. We have a systematic component plus a stochastic component. There's the alternative version where we have y being normally distributed, with mean mu variance sigma squared, and the mean is being moved around linearly by the x's. And then the generalized version that enables there to be any distribution f and any functional form g and any specific quantity that would vary over the observations theta and any set of ancillary parameters alpha, etc. Okay. Right. Let's go to the multivariate normal distribution. So the multivariate normal distribution has an output that is not one number, right? Because the uniform and the Bernoulli and the binomial all had one number that was output. Here it's a multivariate distribution. I'm only going to give you one multivariate distribution right now, which is the multivariate normal distribution. And y of I, or the output of this distribution, is k numbers. Okay, so y1 of I through yk of I, because it's a multivariate distribution. So y of I has k numbers in it. It's a vector of k things, and it's, I'm using looks like the same notation, but you have to know that n here is the multivariate normal distribution, where mu is now a k by 1 vector. So there's k numbers in the mu. It's not just one number. And instead of the little sigma, there's now a capital sigma. So that big thing is a capital sigma. And capital sigma is a k by k matrix. So for k equal 2, there's two mu's, right? Mu1 and mu2. And for sigma, well, there's a 2 by 2 matrix. The diagonal elements from the, actually, let's make this clear to everybody. When we say diagonal with a matrix, it's top left down to bottom right. That's the diagonal. On the diagonal are the variances. So this is the variance of the first variable. That's the variance of the second variable. And off the diagonal are the covariances. Okay. And so the covariances are equal to each other because it's symmetric. Okay. So the mathematical form, that's the mathematical form of the multivariate normal distribution. Sigma is this matrix. Sigma to the -1 means the inverse of the matrix. The pi in here is not a parameter. It's the number 2.141317196841239728 right? Anyway, precision is more valued in this culture than accuracy. So I don't know whether that's exactly the right number, but that's pi, and pi is the mathematical constant, not a parameter. Okay. Simulating ones from this density produces k numbers. We could figure out how to do it, but fortunately R comes with these numbers. There's special algorithms. There's MV, multivariate R norm, which produces these numbers from the mass library in R. Okay. All right. The moments of this distribution, the mean of y is mu, the variance is sigma. Mu is a vector, remember? Sigma is a matrix. The covariance is sigma 1 in the special case of when there's only 2. Sigma 1, 2 is equal to sigma 2, 1. We often see a correlation, which is just a standardized covariance, which is the off-diagonal element, sigma 1, 2, divided by the product of the diagonals. So that's a correlation, and that goes between -1 and 1. And then there's the marginals of this. So the marginals of a multivariate distribution are also normal. That's not always the case for other types of probability distributions, but it is the case here. Okay. And here's just what it looks like. And just to give you a feel for it, so this is truncated bivariate normal distributions. They're truncated just on the interval 0 to 1, just so I can show them to you. If they weren't truncated, each of these would continue on forever, all the way out to the horizon. So I truncate them, although to be fair, I took this from an example. Here the mean is in the middle for both variables. The variables here for this particular picture is beta b and beta w. Could have been. I mean, in the previous page it was y1 and y2, so that's totally fine. Here the mean is low here and high here, and the height basically of this is basically a histogram, but a bivariate histogram. Okay, and the third one on the right here is just a, here I can use this other nice little thing just at the end of this lecture. I just changed it up a little, isn't that great? Anyway, so the thing on the right just has larger variances. The parameters are mu1, mu2, sigma 1, sigma 2, and rho, or sigma 1, 2, however you want to do it, rho being the correlation. Okay, so that's probability. It is not remotely everything you need to know about probability, but it is the essential components from which, if you understand this, we will be able to do much more sophisticated things that are useful for our research, that are useful for making inferences. So next up actually is inference. Next up is reversing probability. Probability is given a model, given a fair coin, what happens, given the multivariate normal distribution with specific parameters, what comes out of it. Inference is much more what we do on a day-to-day basis in research, which is we have a bunch of data. We really want to know what was the data generation process that gave rise to these data. What does that look like? It's not entirely clear because we don't know what the model was. We will assume a model and we'll try to figure out which of the members of the class of models is the more likely one. We will look at the data and try to figure out what model what class of models should we focus on. So inference is the next thing, and I will see you next time. Cheers.